Welcome back everyone. In the last lecture we saw how does location of the closed loop poles affect the response of a system. We saw that if the closed loop poles of a second order system lies on the imaginary axis, then the response of the system is undamped. If the poles lie on the complex part of the plane, basically it has non-zero real part and non-zero imaginary part, then the response of the system was underdamped. If the closed loop poles lie on the real axis and at the same point, then the system is critically damped, and if the closed loop poles lies on the real axis but not on the same point, on the left hand side of the imaginary axis but on the real axis, then the system is overdamped. Now we also saw that using a controller block, a simple controller block which is basically a constant value, we can change the locations of the poles as well, and which means we can change the response of the system. Today we would look into a very important part of control system called specifications. Now, what are specifications? Suppose I am a control engineer and a user comes to me and tells me that, oh, I have this lift, I want to automate the lift such that when you press the key in the lift should move to a particular level, which is what happens in our normal lifts, right? But he wants that it should be exactly to that particular level, and also when the lift rises, the people inside it should not feel discomfort, it should not be too fast, nor the people inside it should feel restless, it should not be too slow. Now for an user, he will just come and say it should not be too fast, it should not be too slow. But as a technical person, if you want to design something, you cannot use this too slow or too fast words to design the system. So you have to come up with a numerical number, you have to come up with some specification that translates to what the users are asking. These are specifications related to the response of the system. In the response of the system, there are parameters which you can use to tell how the system is behaving or how the response of the system is. Instead of plotting the entire response, if you know those parameters, you will know, okay, this is how the response of the system is, and if I change these parameters, the response of the systems will change in some way. So let us go ahead with the second order case itself, okay, and see what are the parameters. Remember, in the first order case, standard first order case, one of the parameters was 1 by t, right? It was the t value, because if I increased the t value, the 1 by t value decreased, which means the pole locations kept on going in a direction, which means that the response of the system would also either be faster or slower depending on how your t is varying. That was the specification. That means if someone comes and tell, oh, this is a first order system, I want it to be fast, that means you will have to change your value of t, which is the specification, in such a way that your response become faster or poles move towards the left of the imaginary axis. Let us do the similar thing for the second order case, and in second order case you will find that there are lot of specifications to look for. Here is our undamped case. So in the undamped case, remember, these were our responses. For zeta equal to 0, the response looked like something like this, which was oscillatory in nature. So the only specification that we have in this case, because the response only depends upon omega n, right? T is anyways varying. So omega n is the only specification. So you can only change the frequency of this system. If you change the pole location of the system, closed loop poles, then the frequency of the system will change. Okay, that is the only specification that you can have here. However, if we move to the next case, which is the underdamped case, so this should have been the underdamped case. So let me just correct this. This should have been the underdamped. So if we move to the underdamped case, which is the case of zeta from 0 to 1. So for this case, the response, step response was something like this, the pole locations were right like this. Now if you look at the response, this is the underdamped step response of the system. So, in case of the underdamped step response, it has a oscillation, but it dies down, right. So, this is how it looks like, and envelope here, the envelope here depends upon this part, right. So, this envelope will depend upon e to the power of minus zeta omega n t divided by root over of 1 minus zeta square, and the sine of omega d t is giving you the oscillations. Okay. Now, here one of the parameters or one of the specifications is the peak time. What is peak time? Peak time is the time taken to reach the peak amplitude. So, the peak amplitude is at this point. So, the time taken to get to this point is the peak time of the response. Okay. So, the question is, how do I find out the peak time? Now, to find out peak time, see, notice that again we go to the mathematical world for this. Look at the response. This response is nothing but a function, right? It is a function of time, and I have to find out the maximum value of that function. How do I find out maximum value of a function or minimum value of a function? I do differentiate the function and equate it to 0. That is what we are going to do. Now, do I know the expression for this function? Yes. Why do not I know the expression? Because this is just the output, right? This is yt, right, as t changes, and that expression is, this is the expression. We have already derived this expression, right. So, that is how we are going to find out the peak time. So, let us try to see that. So, d dt of yt at t equal to Tp at the point, basically at the peak point will be equal to 0. Okay. So, let us try to check what happens. So, if I write down the expression, I will just now go ahead and differentiate this function. So, let us try to differentiate this function. This is a constant. So, differentiation of that will be 0. This part is also a constant, I can take it out. So, I am left with only this part. So, I am differentiating this part, and see, if I go ahead and I am differentiating it, it will give, so differentiation of this will be zeta omega n minus zeta omega n e to the power minus zeta omega n t, and the differentiation of this will be cos of omega d T p plus phi, and you will have an omega d term here. Okay. I am evaluating this at t equal to T p. Okay. So, that is why I have put t equal to T p. So, now if you go ahead and simplify the expression here, omega n, and this expression is nothing but omega n root over of 1 minus zeta square, right, omega d. So, omega n is a positive number. So, I can anyways remove that. So, that is what I have done. So, I am left with minus zeta, then this term will also never go to 0, right. Okay, let me just write it down again. So, for let me just write it down here. So, this is minus, you can go ahead and take this out. This is omega n e to the power of zeta minus omega n T p, and inside you will have zeta sine of omega d T p plus phi minus, what will this be? This will be root over of 1 minus zeta square cos of omega dt plus phi dTp plus phi. This is what it will be. Now, you see, this is equal to 0. So, we have 3 factors multiplied which is equal to 0. So, each of the factors may go to 0. Omega n will never be 0 because we are generalizing this, right. So, omega n is not 0. Now, this is an exponential term. So, for every value of t it will never be 0. At t tending to infinity only it will be 0, and Tp is not infinity. So, now we are left with only this inside part, and that is what is being written here. So, this part is 0, but again zeta is nothing but cos phi. So, zeta is cos phi, root over of 1 minus zeta is sin phi. So, you go ahead and use the formula. So, this is what you will be getting, and finally, you are left with sine of omega d Tp equal to 0. So, therefore, omega d Tp equal to plus minus n pi, right, because this is the generalized solution. Now, notice you are getting n pi. So, n can have values from 1 to anything. So, it can be plus minus n pi. Now, you see, since we are doing ddt of yt equal to 0, I am not only getting the maximums, the minimums as well. So, this expression is valid for this point, this point, this point, each of these points, right. So, the overshoots and undershoots, all those times we can find out from this expression. So, now for the case when n is equal to 1, we will get the expression for this point, okay, because Tp, see here, notice omega d is a positive number here, pi is a positive number, and t we are considering to be greater than 0, right. So, Tp has to be greater than 0 anyways. So, which means from this expression I can directly write omega d Tp is equal to n pi. Now, this can have value Tp equal to n pi by omega d. so this can have many values. So, it can be pi by omega d, it can be 2 pi by omega d and so on. Now, what are these different values? The first value here corresponds to this first overshoot. The second value here will correspond to this undershoot. So, this Tp is given by pi by omega d, which is pi by omega n root over of 1 minus zeta square. So, notice that from the expression itself you notice that the peak time of the response depends upon omega n and zeta. So, if I change zeta and omega n, I change the peak time, the time to reach the maximum value. Okay. So, this was one of the specifications. All this will come together. I mean, there are many specifications. Let us go to the next specification. So, the next specification is maximum overshoot. Now, what is maximum overshoot? You see this response that we have has the maximum overshoot at this point. This is the final value, right? This is the final value of the or steady state value of the response. Why is it the steady state value? Look at the output expression. If you do limit of t tending to infinity y of t, you will get 1, right, because this part will go to 0. This we have talked about earlier also. So, the steady state value of this response of the output is 1. Now, from the steady state value, how much it is going up, maximum that it is going up, overshooting, that is the name, that is why the name is maximum overshoot. The maximum overshoot that we have is what we are trying to find, and the formula will be y max. Y max means the maximum value minus the steady state value yss, which is limit of t tends to infinity yt by yss into 100. This is the expression for overshoot. So, how much you are going up from the steady state value is the maximum overshoot. So, if you find out what is y max equal to y of Tp, because that is the value of the output at the point t equal to Tp. At the peak time, you whatever value you have, that is your maximum value, right. So, y Tp equal to, I just write down this, and then you know what is omega d Tp. From here you see omega d Tp is nothing but pi, right. So, this I can write as pi here. So, sine of pi plus phi is minus sine phi. So, this is what you will get, and finally, what is sine phi? Since cos phi is zeta, so sine phi is root over 1 minus zeta square. So, this and this will cancel out, you will be left with this. So, this is the maximum value that you have, y max here, this is y max and this is the maximum value you have. Okay. What is the steady state value? The steady state value is 1, that we have already discussed earlier also, just limit of t tending to infinity y of t will give you 1. So, then what is MP here? MP is y max is this minus this divided by 1. So, this is what it is. So, we are left with e to the power of minus zeta pi by root over 1 minus zeta square plus multiplied by 100%. So, this is the overshoot of the system. Maximum overshoot is given by this formula, and you see MP is only dependent on zeta, it does not depend on omega n, it only depends on the value of zeta. This is a very important observation, okay, remember this. So, since MP is only dependent on zeta, so if you only change zeta, your MP changes, your maximum overshoot changes. How much overshoot there will be will depend only on zeta, okay. This is a very important observation, whereas Tp depends on both zeta and omega n, okay. Next comes settling time. Settling time idea I have discussed earlier also. What is settling time? See, I mean, it is not possible for the output to get to the exact reference always, right. So, we choose a band within which if the output reaches, then we say that okay, this is fine, we can live with it, okay. Now, that band is always defined by the user. So, generally what we take is if the response reaches to 98% of the desired value or the reference value, then we say that we have reached the steady state value. Okay. So, what is the settling time? So, let us see what is the settling time. Actually, here one important thing is, so although I am saying that a time taken to reach 98% of the desired value, actually it should be the final value. Sometimes the desired value and the final value are not the same. Okay. So, time taken to reach 98% of the final value. I will make this distinction later, but the time taken to reach 98% of the final value is what we are looking for. So, if that is the case, now in this case at least we know that the final value is 1, right, because limit of t tends to infinity yt is 1. So, if the final value is 1, so what we want to see is that when will this response reach to 0.98, right, when will it reach to 0.98 or 0.02. Now, see this when this response is entering this band depends only on this envelope. It has nothing to do with the with these oscillations, only on this envelope. And what is this envelope? We have already discussed. This envelope is nothing but it is dependent on e to the power of minus zeta omega and t by root over of 1 minus zeta square, this envelope. Okay. So, that is why we are saying when is it entering into this band. So, we can find it out by just writing when is 1 minus this expression going to 0.98. So, which will become equal to this expression. Okay. And if you go ahead and try to solve this expression, so this is what you will get. This is the expression that you will get. It is a straightforward manipulation. So, we will get this expression. Again, what is important to note here is that we want to get to 98% of the final value. So, the final value here is 1, right. So, we want to get to 0.98, okay, or 1.02. This is what it has to go inside this band. So, we are just looking at this envelope. This envelope is only dependent on this part, this expression. This has nothing to do with that envelope. Okay. So, that is why we are checking when is 1 minus e to the power of minus zeta omega and t by root over of 1 minus zeta square becoming 0.98. This is what we are checking. So, then we are left with this expression, and so finally, we are left with Ts equal to this expression. This is just a simple taking logs both sides. So, this is what we get. Now, if you calculate this, if you change the value, see, remember this we are doing only from the value for zeta from 0 to 1. So, if you change the values from the zeta from 0 to 1, this upper part of the expression will generally become, this entire thing basically will generally become equal to 4 by zeta omega n. So, basically this upper part is generally nearer to minus 4. So, minus 4 and minus becomes 4 by zeta omega n. Okay. So, this is what is called the settling time of the system. Okay. Remember, we are taking 98% desired value. Someone may come up with different desired value also. 90, I mean, the band depends on the user, but standard practice is we take the 2% band basically. Okay. So, when we say that the band is 2% settling band, so if the final value is 1, I am reaching 0.98, inside 0.98, or I am below 1.02. So, in that band when I am entering, so that is 2% settling band. So, for the formula for the settling time is 4 by zeta omega, approximate formula, but we do not need the exact formula anyways, because this is just a band that we are selecting. So, I can say that is 2.1% also, it is fine, right. So, approximately the settling time is 4 by zeta omega. Now, if someone goes for 5% settling band and do the same calculation, it will come out to be 3 by zeta omega. I am not doing that calculation. So, finally, so for now we are just choosing 2% settling band. So, if it is 2% settling band, our settling time will come out to be 4 by zeta omega. Now, the last parameter that we have is called the rise time. So, rise time is the minimum time taken to reach 100% of the desired value. Okay. So, the desired value is 1 in this case. So, the minimum time that is required to reach the 100% of the desired value is the rise time, and this is nothing but YTR must be equal to 1. The time at which YTR is equal to 1 is what we are looking for. So, if you go ahead and again put this in the expressions, so this is what we will get. There should have been an R here. So, I go ahead and write these, there should be an R here. Finally, this is the expression we will get, because this part will not go to 0. So, we will get this expression, and finally, omega TR must plus pi must be equal to, again I can write here n pi here, because you see it can go to 1 here, it can go to 1 here, there are different times at which the response goes to 1. Okay, but I am not trying to find out all the times, I am just trying to find out the minimum time. So, I will just take the first case, which is the case when this will become pi, this argument will become pi, because if I take 0, of course, someone can argue why not sine of 0 equal to 0. So, if I take 0, so then this becomes plus phi equal to 0, right. Then TR becomes a negative number, because phi in this case is positive. So, that is why we will have omega TR plus phi equal to pi, and therefore, TR will come out to be pi minus phi by omega and root over of 1 minus zeta square. So, you see, for second order case we have got 4 specifications: peak time, maximum overshoot, rise time and settling time. Now, using these 4 specifications we can actually define what the user wants. Suppose the user is saying, I want that the system should be very fast. Okay. Now, what do you mean by very fast? The very first may mean that okay, the user wants that the settling time should be as small as possible, right? Because if the settling time is as small as possible, then that means the response has gone inside that tolerance band that we had chosen, right? Then it has gone to inside that band much faster, settling time is. So then I would like that 4 by zeta omega n must be as small as possible, correct? But it might turn out that when you try to do that, your overshoot becomes very high. What is the problem with overshoot? See, the output we are checking, right? If the overshoot increases, that means the output peak value of the output is too high. Now, if the peak value of output is too high, it might burn out the system also, who knows. So there are, these specifications have conflicts within them also. You are the person as control engineers who will have to resolve those conflicts. That is your work. Okay. So this was underdamped again. Okay. I will end today's lecture here, and then we will take it up from this point forward. Okay. So we have looked into time domain specifications for undamped case and for the underdamped case. For the other cases, critically damped or more specifically the overdamped case, the specifications are not that important because the response has no variation when you change zeta and omega n, because it is always this exponential trajectories. If you look at the expression, you can try it as an exercise. You change the value of zeta and omega n for overdamped case, you will always see a similar response only. However, for the underdamped cases is very what you can say interesting, because zeta and omega n has a nice play here. Okay. So we will talk about all this more in the next lecture. Thank you.